pycnocline density pycnocline, isopycnals, isotherms, isohalides. So effectively what we tend to use is temperature and salinity, which then give us the density, to identify different water masses. And what we have in the oceans is a difficulty in that we have water masses that move, but we have circulations that move. And identifying masses of water and circulation patterns and trying to get an idea of what the two represent is something which you have to sort of get your head sorting out to imagine what these actually mean. And the easiest way is to start with the surface. So this is the surface pattern of the ocean patterns. And you can see we have typical patterns which goes around here, very similar to the patterns that we've seen atmospherically. And we can talk about different water masses, Pacific equatorial, South Atlantic central water, subantarctic water. We can begin to talk about surface water masses in a general term. That doesn't help us an awful lot because that sort of talks about the whole of the North Atlantic. So we need to be a little bit more specific about what we're actually talking about. But each of those water masses, so if we go back to those individual water masses, has a different structure in terms of temperature and salinity. So the North Atlantic has a greater spread than any other water mass of temperature and salinity. But the relationship between temperature and salinity means that it is separate from all other water masses. So if you pick up that density and salinity anywhere in your water column, then you can identify that it is likely originally was North Atlantic central water. So in other words, you can show where it came from. Probably one of the most distinctive is the Antarctic intermediate water. This is water down in the Antarctic, which is very cold and has very low salinity and is uniform in its character. So you can't, this intermediate water is the same. It's very identifiable. Antarctic bottom water, water that is from the very base around the Antarctic, colder, just above zero, around zero, and again a slightly higher salinity. And in the North Atlantic, different from that because it's slightly warmer and slightly more saline, is North Atlantic deep water, which is the same sort of basic idea. And then in the Mediterranean, we're pushed off down here where we have slightly warmer temperatures and very high salinities. But what this means is that in terms of water masses, we can identify separate water masses. So if we were to go somewhere, say let's take North Atlantic deep water. We know where this forms, in the North Atlantic. If you go off South America, say, or South Africa, and you measure the quality of the water column, and you're going through your water column, you measure water that is about 4 degrees centigrade and has this salinity, then you know that that originated from the North Atlantic. So in other words, what you can do is, this sort of water movement you can track on the basis of the characteristics of the water in terms of its temperature and salinity. Because when we talk about the atmosphere, we get to the equator and it either moves north or it moves south. The problem with water is, and the oceans, is that that water can move anywhere across the globe. So if you throw a bottle or throw anything anywhere, especially something that could sink, something, let's say, that was in equilibrium with the water around it and had the capacity to sink, then that could end up travelling around the whole of the globe at different depths as part of the Earth's system. So it's not as if you get the same basic pattern, that the water falls in the Atlantic, north of the equator, it will go to the north, south, it goes. No, it doesn't. It's much more complicated than that. And this is why understanding ocean currents and understanding their past behaviour, because we want to know future behaviour, is so tricky. And this is why we're still trying to understand quite a lot about what these things actually do or how they operate. So water moves. These water masses move according to currents. And these currents, as I've said, can move in one direction at the top of the ocean, one direction in the middle of the ocean, and in a different direction at the bottom of the ocean. So that's why if you're in very deep water and you were diving or something, it's quite possible that your boat at the top could be moving one way in a current and your diver at the bottom could be moved by a bottom current in a total different way. So you could end up sort of waving bye-bye as you go off in one direction at the top, wondering where they've gone, and the other person right at the bottom is wandering off according to a bottom current in the other direction. And that's quite feasible, that can happen. And so it's something which you have to sort of grasp as an idea.